to see how we could derive or how we could relate the 5 kinematic variables, which are displacement, our time interval, initial velocity, final velocity, and constant acceleration. We can now use these 5 equations to figure out some more information about our object. So as a refresher, our 5 kinematic equations are going to be up here. We have our acceleration is equal to final velocity minus initial velocity over time. Our final velocity is equal to initial velocity plus acceleration times time. Displacement is equal to final velocity plus initial velocity divided by 2 times time. Displacement is equal to initial velocity times time plus 1/2 acceleration time squared. And then the last one is final velocity squared is equal to initial velocity squared plus 2a delta x. Okay, so now we're going to look at examples where we are using these 5 kinematic equations. So in our first example, we have a race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. We want to find the acceleration of the car and the distance traveled. So a good place to start with these problems is to figure out what information do we know. So we have a variety of numbers given to us in this problem. So we can see we accelerate from 18.5 meters per second to 46.1 meters per second. What that tells me is that my initial velocity of my object is 18.5 meters per second, and my final velocity is 46.1 meters per second. And that tells us, that this all happens in 2.47 seconds. So my time is 2.47 seconds. The first thing I want to find in this problem is my acceleration. Okay. All right, so I need to go back up to my list and I need to see which equation includes these 4 variables. Which one has initial velocity, final velocity, acceleration times time? And I can see that it's going to be the second equation in green. Okay, so my final velocity equal to my initial velocity, acceleration times time. So once I know what variables I know and what I'm trying to solve for, I can look at my list of equations and see which one has those different parts. Okay, and we picked this one because we know our final velocity is 46.1. We know our initial velocity is 18.5. We're trying to solve for acceleration, and we know our time is 2.4. Once you get here, the physics is over, and it just becomes an algebra problem. So if I want to solve this and get acceleration by itself, my first step is going to be to subtract 18.5 from either side. So 46.1 minus 18.5. So 27.6 is equal to acceleration times 2.47. Divide each side by 2.47. And I'll find that my acceleration here is 11.17 meters per second squared. Okay, perfect. I could have also used this first equation in pink. Either one works because both of those have my 4 main variables in them. Okay, so we can see that this car is accelerating at a rate of 11 meters per second. What that tells us is that our our velocity is changing by 11.17 meters per second each second. Okay. So no, each second my velocity is increasing by 11.17 meters per second. Okay. So that was the first part I wanted to solve for. The second part of this question is asking for displacement, or the distance that's traveled. Okay. So I'm going to pretend like I haven't already solved for my acceleration. Now I'm going to come up to my list and see which one has initial velocity, final velocity, time, and displacement. I can see that it's so in that equation, my displacement is equal to final velocity plus initial velocity over 2 times time. And again, I'm pretending like I haven't already solved for my acceleration. Okay. And I wanted to pick this equation because I'm trying to find my displacement. I know my final velocity is 46.1. My initial velocity is 18.5. Divide that by 2, and then multiply by my time of 2.47. And when I do this, I should find that my car travels a distance of 79.78 meters. So again, we look and see what variables we know, and what equation contains each of those variables will tell us how we will want to solve this. Okay? We can then show this information through a graph. Okay? So if we wanted to make a quantitative position versus time graph, say we start at position 0. At about 2.47 seconds, we will have traveled a distance of roughly 79.78 or 80 meters. Okay? We want to show that we are speeding up during this time frame because our velocities are increasing. So we're going to draw a position time graph where slopes get steeper. And here, I can show that a little bit better. There you go. Okay. I can also make a quantitative velocity time graph because I know my initial velocity is 18.5. That's 20, 40, 60. And after about 2.47 seconds, my final velocity is 46.1. So I can also show that in my velocity time graph. The slope of this line will tell us my acceleration. So when I want to make my acceleration versus time graph, we found our acceleration was 11.17. So since that's a constant value, we'll have a nice horizontal line at 11.17 meters per second squared on our acceleration versus time graph. Okay? So these kinematic equations allow us to make more quantitative or more specific position versus time graph, velocity versus time graph, and acceleration versus time graph. Well, we have a bike traveling at 3.10 meters per second. Then accelerates uniformly to a velocity of 7.3 meters per second over a distance of 35.4 meters. We want to determine the acceleration. So we're going to start this the same way we did the other one. Pick out what pieces of information you know first. So we know initially our bike is traveling a velocity of 3.10 meters per second. It then accelerates to a final velocity of 7.30 meters per second over a distance, or it has a displacement of 35.4 meters. Okay, so pick out what pieces of information we know first, and then we're trying to find our acceleration. So we want to see what equation we know that has these 4 variables in it. So if we scroll back up to our list of equations, we want to see which one has final velocity, initial velocity, acceleration, and displacement. That is going to be this last equation here in purple. Okay? So we're going to want to use the equation that our final velocity squared is equal to our initial velocity squared plus 2a delta. Because we know our final velocity is 7.3. We know our initial velocity is 3.1. We're trying to solve for our acceleration, and we know our displacement is 35. Okay? Again, once we pick out what equation we want to use and plug in those values, the physics is now over. It becomes an algebra problem. Okay? So when we do our algebra for this problem, we'll want to subtract our 3.1 squared from either side, and then we'll divide by 2, divide by 35.4, and we'll find that our acceleration is 0.617 meters per second. So that tells us for each second, our acceleration is increasing at a rate of 0.61 meters per second. Just like the last problem, if we wanted to, we could draw a quantitative position time, velocity time, and acceleration time graph for this motion. For this one, let's just do a velocity time. So for that velocity time graph, we know we start at a velocity of 3. So let's say we go 2, 4, 6. Start at a velocity of 3.1, and we end at a velocity of 7.3. Okay. The reason why the velocity time graphs are super helpful is because we know the slope of this line is equal to our acceleration, which we now know is 0.617. So we know the slope of this line is 0.617 meters per second squared because that's our acceleration. If we found the area of this graph, we know the area is equal to displacement, and we know this object traveled 35.4 meters. So we know the area of this graph would then be 35.4 meters. Perfect. So again, just like our last problem, write out what variables you know first, and then see what equation has those variables and what you're trying to solve for. Next example. So in this example, we have a car traveling 5.5 meters per second. It then hits the brake and accelerates at a rate of 0.3 meters per second squared. We want to see how long it takes for the car to travel 27 meters. So, same with our other problems, we're going to start off by writing what we know. Here we know our displacement for our object is 27 meters. That's how far we want our car to travel. We know initially our car is moving at a velocity of 5.5 meters per second. Okay. It then tells us our acceleration. This is where we need to be careful because if we hit the brakes, oops, I spelled that wrong. That tells us that our object should be slowing down. Okay? So if we were to draw a velocity time graph for this, we know our velocities start at 5.5, and then if it's slowing down, our velocities would decrease and get closer to 0. Okay. This line is super important because it tells us a lot about our acceleration. So we know the slope of this line is equal to our acceleration. If we look at this, we can see that the slope in this case is negative. That tells us the acceleration for our car is going to be negative 0.3 meters per second squared. So even though the problem doesn't say that our acceleration is negative, we know this because if something is slowing down, our velocity and our acceleration are going to have opposite signs. Okay. So if our velocity initially started out positive and it's slowing down, those velocities are going to move downward, get closer to 0. So our slope or acceleration is negative. So make sure you pay attention that when you're slowing down, you pay attention to the sign of your acceleration. All right, so then our goal is to see how long. So we're trying to find our time. So we want to see what equation has displacement, initial velocity, acceleration, and time. And when we look at our options, it's going to be this fourth equation. That displacement is equal to initial velocity times time plus 1/2 AT squared. So displacement is equal to initial velocity times time plus 1/2 AT squared. All right, so we're going to plug in what we know. We know our displacement is 27. We know our initial velocity is 5.5. And we know our acceleration is negative 3. And then we're going to multiply that by t squared. If we look at this, we have t in 2 different places. Okay, so since t is in 2 different places, we're going to have to solve this one a little differently. And we should recognize this equation. If we have t squared, this should remind us of the equation of a quadratic. So in order to solve this, we're going to need to use the quadratic equation. So our first step in solving is to get everything over to one side. So subtract 27. That leaves us with 0 is equal to negative 27 plus 5.5t minus 0.15t squared, okay? Because we did 1/2 times negative 0.3, that left us with negative 0.15. All right, so in order to solve this, we need to use our quadratic equation. And that would tell us that t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. When looking at this equation to see which letters are going to represent a, b, and c, you want to remember that our coefficient from the t squared, that's our a, the coefficient from the t, that's b, and then the coefficient by itself is going to be c. Okay? So with that in mind, we can plug these values into that quadratic equation. And we should get t is equal to negative 5.5 plus or minus 5.5 squared minus 4 instead of 0.15 times negative 27 all over 2 times negative 0.5. Okay. When we plug this in our calculator, we're going to end up getting two answers. We're going to have that t is equal to 5.84 and 30.83. Okay, so even though we get two answers when we plug this into our quadratic equation, we only want to pick one. Okay, because there's only going to be one time that describes this motion where we are braking and slowing down and traveling 27 meters. So we want to graph what the motion of this object would look like on a position versus time graph. So if we were to graph this equation, okay, we're going to end up with something that looks like this. Okay. To figure out which point is correct, we need to think about this. So we wanted to find when our position was 27. So it'll be about there. And again, we can see that there's 2 points where we're going to hit the point or hit a position of 27. This first one being at 5.84 seconds, the second one being at 30.3. So which option are we going to take? What we need to think about is the motion of our car. So we know our car is braking. So our car is slowing down. We want to see which half of the graph pretty much corresponds with slowing down. And we know when we're slowing down that our slopes get less steep. So we can see that the half of our graph where slopes get less steep are going to be the first half. So since the first half of our graph represents our motion, the time when our car is slowing down, we're going to want to pick our first time. So we're going to want to pick the time of 5.84 seconds as our final answer. So if you end up having to do the quadratic equation and you get two possible answers, you'll want to create a position versus time graph for your motion for your car and see which one better fits your scenario. Okay. I hope this helps. Please let us know if you have any questions. Otherwise, I hope you have a great day.